All right, looking at the derivatives of logs and exponential functions, um, let's go ahead and in this one, we don't do a whole lot of proofs in this class, but let's prove a couple of these just because one, the proofs are kind of interesting, I think, and they're pretty smooth and easy to follow. And but the second reason being that they do use a lot of the properties that we've seen before in the chapter. So you could kind of get a kind of neat way to see them at work within a proof. So the first one, so let's go ahead and look at the derivative of a to the x. All right, so before we did e to the x, and then e to the x just equals e to the x. So this one's different in that we have a, so this isn't the log base of e, this is just some number a. All right, so the derivative of a to the x is going to equal a to the power of x times the natural log of a. I'll put a box around this because that's ultimately where we're going. All right, so here we go. Let's so if we're starting here on the left-hand side, so we're going to take the derivative of something, some a to the power of x. Now, if you remember in the chapter, there's some seemingly random properties and identities that they have. And if you were reading through and you're kind of like, oh, that's really weird, why did he include that in there? Well, it's probably because it was important to one of these or relevant to one of these proofs. So one of those things is a to the power of x can be rewritten as e to the natural log of x, e to the natural log of a times x. There we go. All right, so again, a to the x is the same as e to the natural log of a times x. So now let's go ahead and start to work at this one. Looking at this, it looks like we have the chain rule. So we can use the chain rule if we call this, that's our u, right? Well, e to the u, that's super easy. The derivative of e to the u, or the derivative of the outer function, is just going to be e to the u. So that doesn't change at all. E to the natural log of a times x. All right, so then we multiply it by the derivative of the inside function. Well, that's ln of a times x. And I've got, ln of a times a. Nope, ln of a times x. So, and then, so looking at this, I've got some good news. Looks like the natural log of a is just a constant. That's not going to change at all. So we can go ahead and bring that out. So let me rewrite this as e to the natural log of a times x times the natural log of a times the derivative of x. Okay. Even more good news. The derivative of x, that's just 1. All right, so 1 times anything is just the same thing. So because we're multiplying this, I really can kind of just forget about that. Another thing to simplify it, if I look at this, I know that e to the natural log of a times x, well, that's just the same as a to the x. So one last step, looking down here, because that's 1, that goes away. I'm just left with a to the x times the natural log of a, which that finishes the proof because that's ultimately where we were headed. So we started here, we took some derivatives, used the chain rule, and then we ended up right here on the right-hand side. So there you go. That's the proof for a to the derivative of a to the x equals a to the x times natural log of a. Let me see if I can squeeze in one more down here on this piece of paper. So let's go ahead and start looking at some of the logarithm stuff. The first one we'll look at, this one's kind of a neat proof. So the derivative of the natural log of x equals 1 over x. There we go. All right, so let's prove that. Maybe we'll put a little bit of line here, squiggly line, separating those two. So then that way we don't get them kind of confused. Okay, so from the book, there's an identity that they go over that y equals ln of x, or y if y equals a natural log of x, this implies that e to the power of y equals x. So let's start our proof off with that. So we're going to let y equal natural log of x, and we're going to say if this is true, then this implies that e to the y equals x. Okay, so we've started off over here. Now we're going to move into e to the y equals x, and let's start working with this now. So let's take the derivative of both sides with respect to x. So I've got e to the y, derivative of e to the y equals the derivative of x. Implicit differentiation. No problemo, because we are all masters of it right now. Because I'm taking something with respect to x, a derivative with respect to x, of a y. So if you remember from the implicit differentiation lecture, all that means is I take the derivative of this y like I would anything else, and then I just have to multiply it by y prime. So, good news again on this one, the derivative of e to the y, well, that just equals e to the y. And because it's a y, then I just say times y prime. And the derivative of x, well, that just equals 1. All right, and so just like with all other implicit differentiation techniques, now I just solve for y prime. So I do that by dividing each side by e to the y. So I divide e to the y and get it out of there. So now, well, one more step, I guess. And I know from up here that e to the y equals x. So I can rewrite this whole thing, y prime equals 1 over x. And, which is what I'm after, right? So, because the derivative of y prime, the derivative of this, equals 1 over x. So, so there's the proof for the natural log. Let's go over one more quick proof. I'll get some new paper. Not that this next one's like incredibly long and tedious. It's just I don't want to be too far down on that page. It sort of distorts how it looks. So, okay, now let's say that you, instead of taking a natural log, you just want to take the derivative of something log base a. So we're taking the derivative of log base a to the x, and that's going to equal 1 over x times, the natural log of a. All right, so that's an n, sorry. All right, so that, okay. So same thing, let's start on the left and see if we can't work our way to eventually equal something on the right. So I'm going to take the derivative of log base a to the x. And if you remember back to your, back to probably like an algebra class, maybe like a college algebra class, the change of base form just means I can take the natural log of x over the natural log of a to equal this log base a to the x. So I can rewrite this then as 1 over natural log of a times the natural log of x. See, it's the same change of base formula. I just separated it out a little bit because it's going to make it easier down the road. All right, so this 1 over natural log of a, that's just a constant. So I can pull that out in front. So I've got 1 over the natural log of a times d dx of the natural log of x. Well, we just proved this. We just proved that the derivative of the natural log of x equals 1 over x. So I've got 1 over the natural log of a times 1 over x. So then I can simplify this to 1 over x times the natural log of a. And there we go. That's what I'm looking for. So we can see that. Now we take the derivative of this. At the end of the day, it equals 1 over x times the natural log of a. All right. One last thing. I guess you might say, speaking of college algebra, you remember back in that class that you did a lot of these logarithm expansions. And you might have asked yourself back in the day, why do I have to do this? Seems like it, is sort of worthless. Well, today is the day that you'll find out why. So let's say you want to take the derivative of some just like really, really ugly looking natural log. So let's say, how about x times x squared plus 1 squared over the square root of 2x cubed. All right, something like that. And so looking at this, a little parenthesis to finish that off, you might be like, oh, gross. This is going to take me forever to do. Well, not necessarily as hard as it might look because of those definitions that that you went over in your algebra classes. So I got the derivative. Now remember, I can expand this natural log. Anytime I see a multiplication, it's the same as addition. Anytime I see division, it's the same as subtraction. So let's break this natural log apart. So I've got the natural log of x plus the natural log of x squared plus 1 squared minus the natural log, and I'm going to go ahead and rewrite this, of 2x to the half. Maybe one more parentheses in there so that we can keep it all organized. All right, now this is really not that bad, but it even gets better because another one of those laws that we went over back in the day was that I can take these exponents and I can bring them out to the front. So I can rewrite this even easier as ln of x stays the same plus 2 natural log of x squared plus 1 minus 1/2 natural log 2x. Oops, there should be a cubed up there. Now we're really in business. All right, so the derivative of the natural log of x, that just equals 1 over x plus, okay, this one we've got we got a little bit, we've got a little bit of chain rule, but that's okay. So it's going to be the natural log, this will be our u. All right, so natural log of u, that's just 1 over u. So that x squared plus 1 comes to the bottom. And then the derivative of x squared, which is the top one, that's just 2x. 2x to the first. All right, so there, that has that one. And then now on this next one, we're going to have 1/2. All right, looks like we've got a little bit of the chain rule again, but that's okay. We're going to have the same thing, 2x cubed on the bottom, and then the derivative of the inside, that's going to be 3 times 2, that's 6. X squared on the top. All right, so let's keep going. Am I still on? Oh yeah, we're getting down there, but hopefully that's still pretty readable. All right, so I've got 1 over x. 2 times 2 is 4. Over x squared plus 1 minus. All right, let's simplify this one just a little bit. I'm going to be left with just an x on the bottom. I'll have 6 over 4, so that's the same as 3 over 2x. Those x's cancel out. All right. Now looking at this, you could use algebra just to make the denominators all the same and then get it into one fraction, but looks like kind of running out of time on this video, so that's about as far as we'll take it. You can go further and with a lot of the homework, you'll probably want to go a little further than this, but for now, this looks like a good place for us to stop. So remember all the stuff we learned in algebra about these natural logarithms. You're going to use the chain rule a lot with this one, but the nice thing is a lot of this is just learning how to utilize these new derivative formulas that we have.